Hello, this is Coach Eliason. I'm just going to talk a little bit for a review for the thermochemistry test coming up. So I'm just going to go through the different topics on the review sheet. So the first thing that we went over is the difference between heat and temperature. And you should know that temperature, the definition is the average kinetic energy of a substance, and that the definition of heat is the total uh, thermal energy in a substance. So since it's the total thermal energy in a substance, it's very dependent on the mass. And you did a worksheet packet on that, and it asked you about things like a swimming pool versus a hot cup of coffee, and which one would have more heat energy. And even though the pool is cooler because that's so much more mass, it has more heat energy. We did talk about temperature and heat with regard to being intensive and extensive. Heat is an extensive property because it's very dependent on the amount or the mass, whereas temperature is not dependent on the amount. So the temperature of a swimming pool will be the same as the temperature of a small bucket of water taken from the swimming pool. So temperature is intensive property and heat is an extensive property. The next topic we looked at were the properties of solids, liquids, and gases. You should know that solids have the lowest um, kinetic energy and gases have the highest kinetic energy of the substances. You should know that you have to add thermal energy, add heat to change solids to liquids and liquids to gases.
But here, connectivity, high connectivity.
And then we did quite a lot with the equation Q equals mc delta T. The importance of the Q equals mc delta T is that the heat energy is equal to the mass of a substance times the specific heat of a substance times the change in temperature of the substance. And they'll often ask you, what things affect the heat of a substance. And so it's basically the amount of the substance itself, which we regard as mass, and the specific heat, which is really just dependent on the type of substance. So some substances hold heat very well, like water, and some substances release or accept heat very well or conduct heat, and those things we call metals. And then the change in temperature. So a large change in temperature would require more heat energy. So those are explained down here in the definitions. Um, we did use the E equals mc delta T to figure out some properties. So in the lab today and tomorrow, we're looking at E equals mc delta T to figure out the calories in our food. You can use E equals mc delta T or Q equals mc delta T to figure out the specific heat of metals. And you would do that by comparing it to the specific heat of water. We're not doing that lab, I don't think, this year, but it's a good lab. You'll probably do an AP when you take that next year. Going down to enthalpy. So enthalpy is very similar to the Q. It's the heat of the reaction, and it has the symbol delta H, which is the change in heat energy. And you should know that reactions are given a delta H value. And so I put a couple down here on the bottom, really simplified. And so, so if a reaction is endothermic, then energy is needed to cause the reactants to form products. The delta H will be positive, and that will be an endothermic reaction. So anytime the delta H is positive, it means the reactants need energy in order to actually react and form products. The reverse or converse of that is when reactants um, spontaneously react and form products and release energy. In that case, the delta H is negative, and that's an exothermic reaction. Okay, you do have to memorize that delta H is positive is endothermic, delta H negative is exothermic.
This
Okay.
can also be replaced with heat. You could say that too.
Yeah, so the term heat energy could be replaced with the word heat, or heat energy could be placed there. Okay, so
Or a joule's value. Yeah.
okay, so the other big topics were the cooling curves and the potential energy diagram. So
Mhm.
let's go in order. I think we did the cooling curves first. So in the cooling curves, you're looking at the temperature versus time. So as time goes on, you're adding energy to the system. And so you should understand how the cooling curve works. And so the idea is you start with the solid and you have to add thermal energy to increase the temperature of the solid until you get to the melting point.
Mhm.
And then once you're at the melting point, it'll stay at that temperature as you continue to add heat energy but the heat energy will be to stretch the bonds between the solid particles and cause it to allow movement, which is what we define as liquid. So you're going to be going from solid to liquid. Once you get to complete liquid at the end of this phase change, then you have to increase the temperature of the liquid. And so if it were water, you'd be going up to 100, but up here, that's when you'll be going up to the boiling point. And so if it was water, it'd be 100. Other substance boil at other temperatures. But then once you hit the boiling point, all of the energy is not used to raise the temperature, but rather to break the bonds between the liquid particles and change from liquid to gas. And once you have everything in the gas state, then you have to increase the temperature of the gas by adding thermal energy. The cooling curve is the exact opposite of the heating curve. In this case, you actually have to remove thermal energy. So in order to make a gas cool down, you have to pull heat energy or allow the gas to heat something else and thus loses energy itself. So going back to the first one, this is of course an endothermic process, and the cooling curve is an exothermic process. So the gas has to release heat to cool down, and then it's going to release more heat as it condenses, and it's going to release more heat as it cools down to the freezing point, which is the same as the melting point, and then it's going to release energy as it solidifies, and then it's going to release more energy as it becomes a cold solid.
So, Coach Eliason, as we look at this, in what spot are you going to have high and low kinetic energies?
Okay, so of course you'll have the high kinetic energy movement of the gas particles as a gas and more as a hot gas because the gas particles will be moving the fastest, and you'll have the least amount of kinetic energy as a block of ice and even less as a colder block of ice. You do have to know kinetic energy and potential energy in these diagrams, and since temperature is kinetic energy, anytime the temperature is increasing, the kinetic energy is increasing. But at the phase changes, only the potential energy is increasing and not the kinetic energy. So the whole curve has an increase in potential energy, but only the sloped lines have an increase in kinetic energy. The phase changes only have an increase in potential energy. And the last thing that we covered, and we didn't cover it so long, but we did cover it, were the potential energy diagrams, and they do relate to the delta H and the Q. And so the concept here is that potential energy is either gained or lost. And so if you have reactants with a certain amount of potential energy and they end with a lower amount of potential energy, then the difference in the potential energy is the energy given off by those reactants. And so when you have a drop of potential energy, energy left the system. And so
It's going to give you a negative value.
this value here is the delta H, which is the heat of the reaction. So that will be a negative in this case because energy is released.
Mm-hmm.
The distance from the reactants to this top point in that camel hump is called the activation energy. And that's the energy needed to get the reaction started. So you should be able to label the activation energy, the delta H, in these graphs if asked to create these graphs yourself. The other type of reaction is an endothermic reaction, and that's when the reactant started a certain amount of energy, and at the end they have more potential energy. And what happens in that scenario is that energy has to be put into the reactants to give them more energy. So you're stretching the bonds. So whenever the bonds are stretched, which are actually weaker bonds, more unstable bonds, you have more potential energy. It's almost like stretching a rubber band. In this scenario, it has quite a high activation energy from the potential energy of the reactants up to the activation energy before it comes down to some final amount of potential energy for the products. So the distance from the energy of the reactants to the energy of the products is the delta H, and in this case it would be positive, and so it would be an endothermic reaction. And the taller arrow would be for the activation energy, which is labeled up top. I think that's what I'll finish for the review. Good luck on the test.